In this video, we're going to be talking about Lewis structures. So in this video, we're going to be talking about how we can draw Lewis structures for any given molecular compound, how we can tell the most likely existing Lewis structure through formal charge, and the shape and molecular geometry of these Lewis structures. So let's get started. So first, we're going to learn how to draw Lewis structures. So the first thing we have to understand is a few of the rules that we need to know. And let's just quickly look at them. So these are just some of the rules that we should know before we draw some basic Lewis structures. The first one, and perhaps the most important, is octet. So we know that when we draw Lewis structures, we're supposed to be showing covalent bonds. Okay, and so these covalent bonds help the atoms that are being bonded to fill up their valence shell. And the octet rule simply states that any atom that is covalently bonded in a Lewis structure must reach 8 valence electrons. That is the octet rule. And now a couple of the other rules are simply that carbon exhibits 4 bonds, nitrogen most likely wants 3 bonds, and oxygen 2 bonds. And any of the other atoms in these groups will exhibit the same traits. And one of the final rules is that anything in the period 3 or above can exceed the octet rule, meaning that if needed, it can go beyond 8 valence electrons. So with these rules in mind, let's actually look at some practice examples. Now our very first example is carbon dioxide. So mainly, the first steps that we have to take to finding the Lewis structure is counting up the number of valence electrons. So let's consult a periodic table to find out the total number of valence electrons in carbon dioxide. So when we look at carbon, we see that there are 4 valence electrons in its outermost shell. So let's label that. When we look at oxygen, we know that there's 6 valence electrons in its outermost shell. Here, since we have 2 oxygens, we're going to have 12 rather than just 6 electrons. So when we add 4 and 12, we get a total of 16 electrons. So this is the number that we want. Now let's get to actually drawing it. So how we know which atom is going to be in the center is based on its electronegativity. So the more electronegative it is, the less likely it's going to be the central atom. So the least electronegative atom is in the center. So here, carbon will be in the center. So first, let's draw a carbon. And before we do any bonds, let's just draw the oxygens around it. So back in the rules that we just learned, you can pause this and go back and check the rules. We know that carbon will most likely want 4 bonds and oxygen will most likely want 2 bonds. So that really works out in our favor because each carbon or each oxygen can have a double bond towards carbon. So each oxygen will have a double bond towards carbon. And this actually helps carbon as well as oxygen because both oxygens have double bonds and the carbon has 4 bonds. So now that we've done the actual bonding, let's actually draw in the lone pairs. So we know that by the octet rule, each atom will have a total of 8 valence electrons in its outermost shell, meaning that there should be 8 electrons surrounding it. So each bond represents 2 electrons. So let's first look at each oxygen. So the rightmost oxygen, we have 2 bonds, which means we have 4 electrons. So we need to draw 2 more pairs, signifying the last 4. And same with the one on the left. Now we need to determine if there are any lone pairs in the central atom. So the way to do this is, let's first look at the total electrons, which is 16. Let's look at each bonded atom. Each oxygen has 8 electrons through the octet rule. So 16 minus, we know we have 2 times 8 equals 0. So that means we have 0 remaining electrons. So we're basically done here. We know our Lewis structure, and we know that there are no lone pairs on the carbon, so this is our Lewis structure. Now let's go to another example. So we're going to look at water. So for water, we know that we want to find the valence electrons as per our main method. So let's first look at the valence electrons. So first we have oxygen. We know oxygen has 6, and we know hydrogen has 1. Since we have 2 hydrogens, it's going to be 6 plus 2. Which is 8 electrons. Now, let's look at the actual structure. So hydrogen, no matter what, will not be a central atom. So we know oxygen must be the center, and the hydrogens must surround it. Now this atom is polar, and so it should be drawn a little differently, but just to learn the drawing of the Lewis structure, we're not going to get into any of the complicated stuff right now. For now, we'll just do it like this. So we know oxygen wants 2 bonds, and hydrogen only wants 1 bond, because in order to fill its valence shell of 2 electrons, it only needs 1 bond. Therefore, we can put a bond to each hydrogen. Now in this case, oxygen has 2 bonds, which satisfies oxygen, and each hydrogen has one bond, meaning it's filled with valence shell. So hydrogen, each of the hydrogen has two, and each oxygen has lone pairs, which we have to find out how many. So we have a total of 8 minus 2 times 2, which for each hydrogen we get 4 remaining electrons. So then we'd have just 2 lone pairs in the oxygen. And there we go. This is our Lewis structure for our oxygen. Let's go to another example. So PCl5. So this brings up another rule that we learned today, which was period 3 and above exceeding the octet. But first, let's do our main calculations. So we know P will have 5 valence, Cl 7. So if we add the total, so 7 times 5 plus 5 gives us a total of 40 valence electrons. Now our least electronegative atom is P. So we're going to draw that in the center. And the chlorines are going to surround the P, the phosphorus. So now let's draw all the bonds. Now 5 bonds means 10 valence electrons, which means P is exceeding its octet rule. But since it's in the third period, this is allowed. And each Cl, we know that if it makes one bond, it will have 6 remaining electrons as per the octet rule. So simply we're just going to draw that in. And now we have to calculate our lone pairs. So each chlorine will have 8, so that's 8 times 5. And we're going to subtract that from 40, which gives us 0 remaining electrons. And that's it. We're done with this example. So our Lewis structure is like this. So it's just very simple. Now, a topic we have to cover is resonance structures. So essentially, some of these Lewis structures will have multiple ways that bonding can occur. For example, a double bond could be in 2 different places at once. So we'll see that in the next example. But essentially, in real life, the molecular compound that exists is a combination of all the resonance structures. Alright, now let's take a look at the actual example that's involving resonance structures. So let's first draw this as a regular Lewis structure. So we know O has 6, and we know 6 times 3 will give us 18 electrons. Now let's draw this. Since we have 3 oxygens, we'll just put one in the center and the other 2 surrounding it. So let's first draw what we think we should draw. So oxygen will want 2 bonds. So for each oxygen, let's just say that we draw 2 bonds. Now what will happen is, we'll have to do this. So we'll put our lone pairs on the oxygens, so the octet rule stands. Now let's calculate the electrons. So 18 subtracted by, we know each has an octet of 8. So we'll do that, 2 times 8, which gives us a remaining of 2 valence electrons. Now let's draw that in. So here we come up on a actual block because the central atom, oxygen, is not in the third period above, but it actually exceeds the octet rule. So we have to change this up a little bit. So let's quickly erase this and draw it again. So oxygen. Now, instead of doing that, why don't we just put a double bond on one of the oxygens? So I'm just basically trying everything and a single bond here. So here it kind of acts like a halogen with only one bond. Okay, now let's do the calculations. So we have a total of 18 valence electrons, and each oxygen has an octet rule. So it gives us again 2 valence electrons, which we can draw as lone pairs. Now in the center, we have actually a total of 8 valence electrons, which gives us a good Lewis structure, which means everything is in the octet rule and we're all good. So now it brings us up to the topic of resonance structures, because what if this double bond here was in fact here? So what if we just swap them? So that's basically what a resonance structure is. It's basically that this double bond could have been in the left oxygen rather than the right oxygen. So there's 2 different ways that this molecule could have existed, and in real life it's simply a combination. So when we draw the Lewis structure, if you look to the bottom, we just have to draw it like this. So under the bracket, and we have to draw like these arrows indicating that it's resonance. And there we go, that's our answer. So now our final practice example that we're going to tackle is going to be a simple example with a polyatomic ion. This is our final example, our polyatomic ion, which means just a covalently bonded ion. So let's first draw it, and let's find the valence electrons. So nitrogen has 5, oxygen has 6, so 3 times 6 plus 5 gives us a total of 18 plus 5, which gives us 23 valence electrons. Now let's draw. So nitrogen is the least electronegative. For that reason, it'll go in the center. And the oxygens will surround it. So in this case, we have a total of 3. And what we're going to do is we're going to look at the most possible cases for this. So we know that oxygen most likely wants 2 bonds. But we know that if we exceed 2 bonds for more than 1 oxygen, it's going to give us an exceeding octet rule for the nitrogen. So we can only put a double bond on one of them, a single bond on the others. This is nothing related to polyatomic ions, but it's just a step in drawing. So we can assume that this is our valence structure, and let's do the calculations for the electrons. So 23 subtracted by, we know the octet rule exists, so 24, which gives us a -1. Now a polyatomic ion, so since this ion is a charge of -1, our total valence electrons should end up as -1, since it is a polyatomic ion. Okay, so that means this will have a charge of -1, and if we got a case which was 23 minus 23 equals 0, that would be wrong, because we have to end up with -1, since negative charge means that one more electron is being added. So this is how we draw the structure for a polyatomic ion, by using brackets and indicating the charge outside. And now we are done. So this is how we draw Lewis structures, and now we will be covering formal charge. This is the second part of Lewis structures, which talks about formal charge. Formal charge is basically the charge assigned to an atom in a molecule, assuming all electrons are distributed equally. And formal charge is important because it determines the most accurate Lewis structure in a molecule. And figuring formal charge is actually pretty easy. So formal charge is basically the number of valence electrons minus the unbonded electrons minus the number of bonds in the molecule. So if we look, for example, in a molecule of water, which is oxygen bonded to 2 hydrogens, and it has 2 lone pairs of electrons. Oxygen has 6 electrons, so it'd be 6 minus the number of unbonded electrons, which is 4, minus the total number of bonds, which is 2. And that gives a formal charge of 0. And that's pretty much it. So let's look at some more practice problems. So now let's look at some practice problems which involve finding the sulfur atom with the formal charge of +2. So the first example is SF6. So sulfur atom has 6 valence electrons. In this case, it has no unbonded electrons, so it's -0, and minus the total number of bonds, which is 6. And that gives a charge of 0, which is not correct. It's not +2, so that's the wrong choice. Now we look at H2S. The sulfur atom, once again, has a number of valence electrons is 6. The unbonded electrons are 4, and number of bonds are 2, and that also gives a formal charge of 0. And in the last example, sulfur atom has 6 valence electrons. It has no unbonded electrons, so -0, and then minus the number of bonds is 4, so that gives a charge of +2. In this example, we need to determine the correct Lewis structure for CNO negative. In order to figure out the correct Lewis structure, we need to find the formal charges of each of the atoms. And why is that important? Well, if we look at a molecule, it is generally the electronegative atoms that have a negative formal charge. Why is that? Because electronegative atoms have a stronger pull towards electrons, which contain a negative charge. So by figuring out which structure, which electronegative atom has a negative formal charge, we can determine the correct Lewis structure. So in the first example, oxygen is the electronegative atom. Oxygen has 6 valence electrons. We can subtract the 6 number of bonded and -1, which gives -1. So straight away we can see the oxygen here has a formal charge of -1. If we look at the second example, oxygen has 6 valence electrons, minus the 4 unbonded electrons, minus the 2 bonds, which gives 0. Now generally we want atoms to have the lowest possible formal charge, which is close to 0,
but because oxygen is negative, we would expect it to have a negative formal charge. So that's why we would still prefer the first one. And in the last example, oxygen has 6 valence electrons, minus 2 unbonded electrons, minus 3 bonds, which gives +1. And this would be incorrect because oxygen should have a negative formal charge instead of a positive one. So we can see that the first structure of CNO is most likely the correct one.
Thank you guys for watching this video. We hope you guys learned something from it. If you want to see more related content on many other APs, make sure to like this video and subscribe to our channel. Thanks again for watching this video, and we'll see you next time.